During an earthquake, when the ground begins to shake, we often hear terms like magnitude 7.2 or intensity 6. But what do those numbers actually mean? How do scientists calculate them? And why does the same earthquake gently shake one city, while completely destroying another? Let's break it down in the simplest way possible. Welcome to Earth Diary. Today, we're uncovering how scientists determine the true power, the real scale, of an earthquake. Watch till the end, and don't forget to like, subscribe, and tap the bell icon so you never miss an update. Let's start with the basics. When an earthquake hits, it sends vibrations or the seismic waves through the earth. These waves are recorded by seismometers. Each seismometer senses the ground shaking, magnifies that tiny motion so it's easier to measure, and then records how the shaking changes over time. These instruments are extremely sensitive, and can detect earthquake waves that last from about 0.1 to 100 seconds, even from quakes that happen thousands of kilometers away. From this recorded data, scientists can figure out three important things: when and where the earthquake happened, and its size or true power, that tell us how destructive it might be. Earthquakes can be very different from one another. Some shake the ground violently, while others are so mild that we barely notice them. To understand the full picture of an earthquake, that includes the total energy released, and the damage it can cause, scientists developed two ways to measure an earthquake's size. The first measurement is intensity, which shows how much the ground shakes at a specific location, and how much damage it causes. With the invention of seismographs, it became possible to actually measure the ground's motion using instruments. This measurement, calculated from seismic records, is called magnitude, and it represents the earthquake's true power at its source. Both intensity and magnitude give important, but different, information about an earthquake's strength. That's why scientists use both to fully describe how severe an earthquake is. Before modern seismometers existed, intensity was the only way to measure earthquakes. Scientists estimated it, based on how strongly the ground shook, and the amount of damage observed, which was mostly a subjective judgment. In 1902, Giuseppe Mercalli developed a more reliable way to measure intensity, the Mercalli Intensity scale. This was a simple 10-level scale, that focused on the effects people felt and the damage caused. Later, it was modified into the Modified Mercalli Intensity or MMI scale. The MMI has 12 levels, ranging from faint shaking to catastrophic destruction, and uses Roman numerals to designate intensity. The Modified Mercalli scale doesn't have a mathematical basis, and it is subjective, relying on observed effects. The lower levels describe how people feel the earthquake, while higher levels are based on structural damage, and usually engineers provide information for levels 8 and above. Traditionally, intensity data was collected from people via postal questionnaires. Today, the Internet is used to gather this data online, for example through "Did you feel it?" questionnaires. The MMI scale is mainly used in the United States and New Zealand, but other countries have adapted versions. That's because earthquake intensity differs from place to place, and depends on many factors like the distance from the epicenter, depth of the earthquake, direction of rupture, building design, and type of ground beneath structures. For example, a single earthquake can produce many different intensities. Shaking is usually strongest near the epicenter and weakens with distance. The type of ground also matters. Soft sediments shake much more than hard rock. Because of these variations and its subjective nature, a single intensity scale cannot be applied to the entire world. Enjoying the video so far? Hit like, subscribe, and stay with me, there's a lot more to uncover. So, the second way to measure an earthquake is its magnitude. This is a single number that describes the earthquake's true energy release. This value comes from seismograph recordings, not observations. And as it's calculated using precise instrument data, the magnitude stays the same everywhere. Magnitude is written in whole numbers and decimals. A magnitude 5.3 is considered moderate, while a 6.3 is strong. Basically, it's a standardized, logarithmic calculation based on seismograph data, adjusted to represent the earthquake's total energy release, as if it were measured at a fixed reference distance. So, even if people feel the shaking differently in different places, the earthquake itself releases a fixed amount of energy, and that fixed energy is what we call its magnitude. Thus, when the news reports, a magnitude 7.2 earthquake struck the city, that number describes the strength of the earthquake at its source, not how the shaking felt in any one location. In 1935, American seismologist Charles Richter created the first magnitude scale. You've probably heard of the Richter scale, but it's not commonly used today, except for measuring small, local earthquakes. Richter's method was straightforward. He measured the largest wave amplitude on a seismogram, corrected it for distance that is standardized to 100 kilometers from the epicenter, and applied a logarithmic formula to get the earthquake's magnitude. Because the scale is logarithmic, every 1 unit increase means the shaking amplitude is 10 times larger, and the energy released is about 32 times greater. For example, a magnitude 6.5 releases 32 times more energy than a 5.5. While a magnitude 8.5 releases millions of times more energy than tiny quakes people can barely feel. However, the Richter scale works best only for small to moderate earthquakes. For very large earthquakes, it begins to saturate. Saturation means that beyond about magnitude 7, the scale cannot properly show differences in energy release, making huge earthquakes look similar, even when they are not. This happens because the Richter scale is based on the peak amplitudes of high-frequency seismic waves. In very large earthquakes, the quake lasts longer and covers a much bigger area, producing more low-frequency, long-period waves. These don't produce large amplitude on seismograms. So the Richter scale, which relies mainly on wave amplitude, fails to capture the true size of giant earthquakes. Because of these limitations, scientists developed a more accurate and universal system, the moment magnitude scale. Today, the moment magnitude scale is the most accurate and widely used scale for measuring earthquakes around the world. It tells us the total energy released during an earthquake. Unlike the old Richter scale, which only worked well for small to medium earthquakes, the moment magnitude scale works for all sizes, even the largest earthquakes. It also does not saturate, meaning it can measure giant quakes correctly. MW is calculated using several factors like how much of the fault slipped, how far the ground moved, the strength of the rocks, and detailed data from modern seismographs. Its accuracy can be understood with a simple example. Two earthquakes marked 8.3 on the Richter scale. But when scientists used the moment magnitude scale, the 1964 Alaska earthquake was upgraded from 8.3 to moment magnitude 9.2, because it released far more energy than originally measured. And the 1906 San Francisco earthquake was downgraded from 8.3 to moment magnitude 7.9, because it released less energy than first thought. This shows why MW is more reliable, as it reveals the true power of an earthquake. So, that's how we determine the scale of an earthquake, using both intensity and magnitude, two measurements, that together give us the full picture of how strong an earthquake was, and how it affected the world around us. If you found this explanation clear and helpful, make sure to like the video, subscribe, and hit the bell icon. Thanks for watching.